Hey chemists, in this lesson we're going to look at how we relate the electrochemical potential of a cell to the change in Gibbs free energy. It's based on this equation, which is negative NFE, where N is the moles of electrons. That's when we write out half reactions, and after you balance them and normalize the electrons, it's how many electrons are in each half reaction. You'll see what I mean when we actually do it. This fancy script F is Faraday's constant, named after Michael Faraday, which is 96,485 coulombs per mole of electron. We took the fundamental unit of charge that you might have seen in your physics class, which is something like 1.6 times 10 to the negative 19 coulomb per electron. You multiply that by Avogadro's number, and you get that. So we just made it per mole. So if it's different than the one you've seen in your physics class, that's why. And this E with the superscript 0 means standard voltage, standard potential. We'll say voltage, which we get from tables of half reactions. So let's see how we use this right away. Using standard potentials, find delta G standard for this redox reaction involving copper 2 and iron becoming iron 2. For each one, let's write out the half reaction that occurs. Looks like copper 2 gets reduced to copper, and iron metal gets oxidized to iron 2. So copper 2 gets reduced with 2 electrons. I'll just write red to remind me that that's what's happening, to copper metal. And iron gets oxidized to iron 2 and 2 electrons. Already balanced. 2 electrons gained, 2 electrons lost. The potential, if you look up in the table, the reduction of copper is positive 0.339 volts. The oxidation of iron, you have to find the reverse of this in the standard reduction potential list. Once you do that, you negate it. It actually becomes a positive number, 0.409 volts. That's just from tables. So we add the reduction potential plus the oxidation potential, and we get the standard potential of the cell. That is 0.748 volts. And now we can use our new equation for today. That's delta G standard is negative NFE standard, which is negative 2 moles of electrons. That's because we have 2 electrons in the half reactions once they're normalized. And then Faraday's constant is 96,485 coulombs per mole of electron. And then we have the voltage, 0.748 volts. You might remember from your physics class, a volt is a joule per coulomb. So I'm actually going to write it as 0.748 joule per coulomb. And when I do that, we can calculate what we get. It'll be in joules. That gives me negative 144,342 joules. And we'll just turn it into kilojoules and round to 3 sig figs because we have 3 sig figs in the voltage. We're not going to use 1 sig fig for the mole of electron. That's always a whole number. So you get negative 144 kilojoules. Notice delta G is negative, so this reaction happens in the forward direction, and that's consistent with the fact that the potential is positive. And that's the main thing that this new equation tells us. A negative delta G goes with a positive electrochemical potential. And this is how we use Faraday's constant, just to change the potential into an actual voltage. Speaking of Faraday's constant, I'll show you a very quick clip from an episode of The Simpsons where Mr. Burns is nostalgic and about to buy a comic book store, and he makes an offer. And now that you've seen today's lesson, you'll know why it's funny. So here's his clip.
How much for your entire collection? The speed of light expressed in dollars.
Just give him Faraday's constant.
Ha! There's Faraday's constant right there. 96485, even to the 0.34 as he makes it out. So that season, good writers to know that that was Faraday's constant. Alrighty. So that talks about potential and standard conditions for delta G. What about non-standard conditions? What do we do if we're not at 1 molar and not at room temperature or 1 atm? Sorry, 1 atm or 1 molar. That's when standard conditions applies. For this, we're actually going to go back to another delta G equation. So remember, delta G under any conditions is based on delta G standard plus R times the temperature times the natural log of the reaction quotient, Q. And if we take our new equation from today, negative NFE, and substitute that for each of these delta G's, we get on the left-hand side negative NFE, non-standard, is equal to negative NFE standard plus RT ln Q. And that rearranges to something that you actually have on your reference table called the Nernst equation, which looks like this. I'm just going to box it. So this shows us where the potential of the cell under any conditions is based on the standard conditions, the temperature, the R constant, the moles of electrons, Faraday's constant, and then the reaction quotient, which is the same expression as the equilibrium constant, just not at equilibrium. Speaking of equilibrium, we'll make a couple of reminders. At a state of equilibrium, recall that delta G is equal to 0. That means E is 0. And what happens is K is equal to Q. Q is equal to K. And if we apply that, that means we can actually relate the equilibrium constant to potential. And we actually get a whole other equation. I'll squeeze it in up at the top here because it's quite useful. It says that if we, imagine doing that. Let's change this to equilibrium. Then this Q becomes K, and then this becomes 0. So you have just this right-hand side of the equation. You can set them equal to each other. And if we rearrange and solve for E standard, we get E standard is equal to RT natural log of the equilibrium constant divided by Faraday's constant times the moles of electrons. So here's the non-standard equation, and then here's a nice equation that relates K to the standard potential. So we'll use both of those as we move forward. So let's try this. What do we do with a situation where we're under non-standard conditions? Here's a redox reaction, and what they've done is they've shown us how the molarities are not 1 molar. Remember, the reaction quotient is just based on things that are aqueous. It doesn't include things that are solids, so it's not about how much of the solids I have. As long as I have some, this reaction can go. But we can calculate the reaction quotient from these non-standard molarities, which are just not 1 molar. I'll do the same thing I did up above. I'll start by writing the half reactions. Manganese 2 gets reduced with 2 electrons to become manganese. I'll need the standard potential. So that standard reduction, if I look it up, it's actually negative 1.182. And then the aluminum is an oxidation. Aluminum will get oxidized to aluminum 3 plus and 3 electrons. And the oxidation, you look up the reduction, you flip the sign, you get positive 1.68, and you add the 2. We get the standard. Potential for the cell is 0.50 volts, just round to the hundredths place. Why did I do that? Well, I need that in order to get the non-standard potential. Find the non-standard potential. So the non-standard potential E is equal to the standard potential, 0.50 minus R, 8.314 joule per mole Kelvin, T, 298, all over N times F. What's N? Well, look at the electron count for those two half reactions. I'm not going to write out what it looks like once it's balanced, but you should be able to tell. You'd have to triple the reduction and double the oxidation. So those electron counts are going to become 6. And then Faraday's constant, we just learned, 96485. What about the log of the reaction quotient? Well, the reaction quotient is going to be products over reactants. If you just picture the expression, it's aluminum in the numerator and manganese in the denominator. So I have 1.5 divided by 0.5. But don't forget those coefficients. You'll have a coefficient of 2 and 3 that respectively become your exponents. So I have a big, lengthy equation. When I plug all that into my calculator, I get an E of 0.49 volts. It is ever so slightly smaller than standard. And that's actually something that we can make sense of. E is less than E standard. And that makes sense if you think about Le Chatelier's principle. Compared to 1 molar, we have less reactant and more product. So this reaction is actually being stressed to the left compared to 1 molar. If a reaction is being stressed to the left, to go in reverse, you're going to get less voltage. You're going to get less out of this reaction. So more product and less reactant shifts left, thus lower voltage. We'll see that a lot of the questions that come up about this topic can be explained using Le Chatelier's principle, just to qualitatively predict what the voltage will be compared to standard conditions. Okay, so that's is new for today. I'd like you to hit pause and see if you can figure out the next 2 questions, keeping Le Chatelier's principle in mind, considering this aluminum and manganese reaction. What do you think is going to be true if we have these molarities and respectively these molarities for that same reaction? And then see if you can apply this to a different reaction. Here's a couple of half reactions that are both reductions. What's the balanced reaction, what's E standard, and what's K once you've done that. So hit pause and try that now. Okay, welcome back. So zooming in on this, predict if E is larger or smaller than E standard for each case. Well, E standard is 1 molar for each, but here we have a higher concentration of product, higher concentration of product. So that means the reaction shifts left. So E is smaller. Less forward reaction will lead to a smaller electrochemical potential. And if you look at B, it's pretty much the exact opposite. B has a higher concentration of product. A higher concentration of reactant. Higher concentration of reactant. And the other thing is still 1 molar, so that's still standard. So that means the reaction shifts forward. Thus, E is bigger. More forward reaction, more potential, more voltage that we can get out of this. And then the other problem that I asked you to do is to use these half reactions and balance. To do that, we have to first figure out who's getting flipped, although you can actually tell because they have a skeletal of it right here. We're going to keep the first half reaction as a reduction. We're going to use the second one as an oxidation, which means we need to flip it And then to normalize it, we're going to have to multiply that by 2. So I get 1 S4O6 negative, 2 chromium 2s, 2 chromium 3s, and then 2 thiosulfates, S2O3 negatives. To get the E standard, you simply add the two potentials, 0.17 for the reduction, plus positive 0.50 for the oxidation. So we get 0.67 volts. And then to get the equilibrium constant, we're going to use the equilibrium constant equation that's buried in this, related to the potential. We're just going to rearrange that and solve for K. I'll start by solving for the natural log of K. The natural log of K is NF E standard all over RT. In this case, N is 2. F is 96485. E we just got 0.67. R 8.314. And T 298. Notice R is 8.314. It's not 0.08206. That's just for PV equals nRT. That's when you use that R value. They're actually interconvertible by a unit conversion, but we almost always see 8.314 with all these things that have joules in them. You do some calculator skills, and you'll get a value of K that's 4.6 times 10 to the 22. Which also is consistent with the other things we've seen, a positive voltage and likely a negative delta G. Aha, we're going to have a large value of K, again showing that the reaction is going forward. It is favorable of the products, as it's product heavy at equilibrium, we should say. Okay, lastly, in terms of calculating voltages, there's a special thing that's not normally seen on the AP exam, but I find it quite fascinating, so I like to teach about it. It's called a concentration cell, and it demystifies the fact that you need two different metals to make an electrochemical cell. You actually can still build a cell and create a potential difference even though the metals are the same. I remember learning in my high school chemistry class, perhaps incorrectly because it was me, but I remember learning that you always needed two different metals, metal A and metal B, and that's not the case. They can actually be the same metal as long as they're in solutions that are of different concentration, hence the name concentration cell. Here, let's make a note. The higher molarity is the reactant. And I'll show you what I mean by that. So what reaction is actually happening? Well, it's iron becoming iron 2, and then it's iron 2 becoming iron. So it looks like no net reaction, but because of the concentration gradient, there is a reaction. We have iron oxidizing to iron 2 plus 2 electrons, and we have iron 2 plus picking up 2 electrons and getting reduced to iron. I don't even know what those half reaction potentials are, but if I look them up, they're going to be the reverse of each other. So I know my standard potential is 0, and that's always true for a concentration cell. But there is actually an overall reaction here. They don't all cancel out because these iron 2 pluses are not the same. They're different molarities. So we write it as iron 2 plus with the higher molarity, in this case 0.1 molar, reacts with the iron that it's in contact with to make iron 2 plus at a lower molarity, 0.01 molar in this case, plus the iron that it's in contact with. That's the actual reaction. So the reduction is happening on that more concentrated side. Fe2 plus is getting reduced to Fe. On the other side, we have Fe getting oxidized to Fe2 plus. That's your respective reduction and oxidation. That means we know where our anode and cathode are, because cathode is the site of reduction. So this is the cathode on the right. And anode is the site of oxidation. So this is the anode on the left. And electrons always go from anode to cathode. So the electron flow is from left to right through the wire. And there's even one more designation, which is the source of electrons, which happens to be the anode, because it's losing electrons on this side, and electrons are going into the wire from here. We give this side a negative symbol. They don't use this that often on the AP, but if you see it, and you'll certainly see it on a real battery, this is what the designation minus and plus refer to. Refers to the source of electrons at the anode and the pulling in of electrons at the cathode. What's the potential for this? Do we get any volts out of this? Yeah, we do. This is non-standard. So E is E standard minus RT over NF, natural log of Q. And if we plug in up above, E standard is 0 minus 8.314 times 298 all over 2 moles of electrons times Faraday's constant, 96485, times the natural log of, let's see, the product over the reactant, which is 0.01, all over 0.1. And if you do that, you get a pretty small potential. It's only 0.03 volts, but it's non-zero and it's positive. Note, if you accidentally reciprocate the Q value, you would just get a negative number and know you made a mistake. The cell potential is always positive for a concentration cell because that Q ratio is always a fraction. So the log of a fraction is a negative number, and then a negative number times a negative number gives you a positive potential. So that's how a concentration cell works. Okay, just one last thing for today. We'll wrap up. We're going to do a practice AP question here. Take a look at this. This is meant to be done without a calculator, but here's 2 half reactions based on the information above. See if you can figure out what the delta G standard and the E value would be just on paper, but without a calculator. Okay, so first let's get the E cell, the standard. The standard would be, we're going to flip the first one and keep the second one so that we get a positive number. So 2.37 minus 0.74. On paper, you can get that as 1.64 volts. So, sorry, 1.63 volts. So we can eliminate choices C and D. How do we get the standard delta G value? Well, delta G is negative NFE standard, which is negative. Our electron count, if you look at the electrons, we have 2 and 3. So once normalized, it's going to be 6. Faraday's constant, 96485. And then the E standard of 1.63. And here's where you could go, how the heck am I going to do this without a calculator? Well, you've got to approximate. I mean, we've got to do some simplifications. I'll keep the 6. The 96,000, I'm going to round up a little bit and call it 100,000. The 1.6, I'm going to round down a little bit and call it 1.5. And I'm also noticing, they want this in kilojoules. If I leave this, I'm going to get it in joules. So really, I'm just going to divide by 1,000 right away, and I get negative 6 times 100 times 1.5. So I'm trying to calculate more or less in my head negative 600 times 1.5. Well, that's about negative 900 or so. So between the remaining choices, A and B, I can safely conclude that it's B, just based on rounding. So that's how they might assess us with this on the written AP exam. Okay, that's how we get non-standard potentials using the Nernst equation, and how we deal with Le Chatelier's principle related to electrochemical cells and a concentration cell.